All right, so we're going to pick up where we left off last class, but before we get into all of that, I just wanted to make a point about some of these problems. I think this is what you just ran into, and I know a lot of people will run into similar things. When it comes to math, it is really easy to overthink these problems. Avoid that. And I know that's like speaking out of the side of my mouth, like, okay, thanks for telling me that. I know to avoid overthinking things. What I mean is, if you get stuck on a particular problem, think about the fundamentals of math, the foundation. Your rules like distribution, associativity, commutativity, things like this, and see if you can build up from those rules how to do the problem. A lot of times that's where we start to overthink, is we get into a problem, we're like, oh shit. Can I just do this the normal way? Probably, yeah. Like there's very few times where things like associativity, commutativity, the distributive properties, power properties, etc. There's only a few times where those rules don't hold up. And usually that's only when you have something like dividing by a zero. So having said that, just something to keep in mind. But jumping into what we were talking about last class, we had we had seen that looking at the derivative, we can get some general information about what our function is doing, right? And we can get this information by first identifying what are called critical points. A critical point is a point, an x value, where the derivative of your function is either 0 or it doesn't exist. In this particular problem, you have a critical point at 0 and a critical point at 1. These critical points then let you break up the number line into different sections. From there, the trend of your function in these sections, in these intervals, they're going to be the same. So it's enough just to say, let me pick one point out of one of these sections, out of one of these intervals, and see if my function is increasing at that point. If it is, then everything in that section has to be increased. So here, we've got 3 different sections. Negative infinity to 0, 0 to 1, 1 to infinity. And in all 3 of those sections, your function is going to be doing the same general thing insofar as it's increasing, decreasing, or increasing again, right? This is, again, what your critical points tell you. So, here, it's enough to say, in this first section, let's pick one point, negative 1, and check to see if the derivative of my function is negative or positive. In this case, since our function is increasing, your derivative is going to be positive. In that second section, let's choose a point, maybe 1/2. Your derivative is going to be negative there. And then in that third section, your derivative is going to be positive, no matter what point you check. And that's what these critical numbers are doing. They're breaking up your function or your number line so that you only have to check one point in each of those sections to know if your function is increasing or decreasing. That's why these things are so important. And again, the critical number is a number that the derivative of your function comes out to be 0 or undefined at. Everybody cool with this? All right. So, having said all of that, let's jump into section 3.2. 3.2 is all about relative extremes. We already talked a little bit about this. Trying to remember what slide exactly we ended on. But like I said, we've already talked a little bit about this. What a relative extreme does is it gives you the ability to check if that critical number correlates with a peak or a trough. If that critical number is a peak, then take your x value and jiggle it around that critical number. Every value that comes out of your function when you jiggle that x value, they're all going to be less than what they are at that critical number. So what I mean is, let me draw a graph. Probably can't see that, I assume. So I'm going to draw it in red. I have an eraser. Why do I always use my hand? All right. So here, we're going to have two critical numbers in particular. Let's call this C1. Let's call this one C2. Notice everything to the left of C1 is increasing. So the derivative of whatever your function is going to be positive before you get to C1. Everything between C1 and C2 is decreasing. So all of those x values, your derivative will be negative. And everything after C2, well, it's always increasing. Always increasing. So your function, the derivative of your function will always be positive. Now, we want to know if C1 and C2 correspond with troughs or peaks, valleys or peaks, without graphing this thing. We know graphically, yeah, obviously this is going to be a peak and this is going to be a valley, but let's say we just know the function. Well, first we're going to say, what is our function at C1? Blah. Now we're going to say, all right, pick a couple of x values close to C1. Take a collection of them right around C1. Let's say this is A. Say that's A, that's B. We're going to pick a bunch of values in between, not including C1. If those values are all less than what your function is at C1, so what I'm saying is, let's pick some x value between A and B and not equal to C1. If all of those x values, your function is less than your function at the critical point, that's a peak. Make sense? Because if you're at the peak, then everything around it should be less than it. Going uphill, you get to the top, you're going back downhill, right? And that's what we're saying here. Similarly, here, all the values will be larger than what they are at f of C1, right? So for this reason, it's enough just to say, pick a small group of A and B's around C1, around your C, and see if your function is larger or smaller. The end. Make sense?
So the right side is the relative maximum, and then this bottom left is relative minimum? Is that what you're saying? Like on your graph?
Yes,
Maximum,
yes.
minimum. Yeah.
And what this word relative means mathematically, this actually brings up a good point, is it's not the maximum for everything, right? Like come over here, this f of C1 is smaller than somewhere over here, right? And we might have a point lower than FOC2. What we're saying is that for the numbers immediately around it, it's max or it's min. So, having said that, one way we can check this is by checking the behavior of your derivatives. Notice if you have a relative max, then your derivative has to go from positive to negative. If you have a relative min, your derivative has to go from negative to positive. And this makes sense because you're going down and then back up, right? Or up and back down. Just like walking up that hill. So instead of checking a bunch of these x values, because that takes some time, right? First you have to figure out what x values to check. Then you have to pick your x value and actually check it. Then you have to say, all right, what about another x? And keep doing this. It takes some time. Instead of doing that, you can check the derivatives themselves. And what's convenient, what's interesting about these relative extremes, they're going to correspond to these critical points. And if we think about what the critical points tell us, that makes perfect sense, right? Because a critical point tells you when your function flattens out a little bit, right? For just a brief moment, or when it's a cusp. Generally just when the behavior of the function changes in some way, shape, or form. So the critical points don't necessarily have to be a relative extremum, but a relative extremum has to be a critical point, right? It's just because you have this thing undefined doesn't necessarily give you that it's an extremum. It could be something like, trying to think of a good example. Could be something like this. If your derivative looked like this, like the tangent function, then you'd have a relative extremum right here. That doesn't necessarily mean that you have a max or a min, right? Everybody get that? Cool. Cool. All right, so to check using derivatives whether or not your critical number is a relative extremum, like I said, it is enough to go back to what your derivatives are doing. Let's say we just care about our function inside of an interval. You're going to have a critical number here, that's C. So it's enough to say, hey, between A and B, our derivative here is negative, our derivative here is positive, so this has to be a min. Cool. Similarly, we can go the opposite route with the max. And then if it just stays constant, if the derivative goes from positive to positive or negative to negative, it's not a max or a min. And we'll get into that case later. So looking at some of this, just a couple of quick examples. Here, We have negative to positive, corresponds to a min. Here we have positive and negative, corresponds to a max. Here we go from positive to positive, doesn't correspond to anything, right? It's technically flat at that point. Goes from negative to negative, again, technically flat at that point. At that one single point, it literally just moves to the next point over. So as a quick example, because these problems take forever, I just posted the entire thing all at once for us to look at them. We start off with our function, f of x is equal to 2x cubed minus 3x squared minus 36x plus 14. We're going to take the derivative of that. Well, everything here has a factor of 6, so let's go ahead and pull that out. Then we can factor it out further. This thing factors out quite nicely, and we set it equal to 0. And we find that we have a critical number at x is equal to negative 2 and at x is equal to 3. So we need to check on either side of negative 2 and of 3 to determine whether or not these correspond to peaks or troughs. Looking at this, if you had a guess, which is which?
Would be a trough.
Which one's a trough?
Great question.
Negative 2 or 3?
Negative 2 would be a trough and 3 would be a peak.
I'm gonna guess it's gonna be reverse, but it's because of the sign on the highest order term.
Okay.
But I don't actually know that right off the top of my head. Without like graphing this out, I don't know. So we've got our critical numbers. Now we're gonna break everything up into 3 intervals. Negative infinity to negative 2. For those of y'all at home, you can pull up the exact slides that we're looking at. You should be able to. Oh no. Is that frozen? That is frozen. Weird. Give me just a second here, folks. Something weird is going on with the screen share. I did not realize that at first. Stop share. There we go. All right. So what we're looking at, like I said, for folks at home, you can click over to the view of the slides themselves and see my cursor moving around to see what it is I'm pointing at. Like I said, our function here is equal to 2x cubed minus 3x squared minus 36x plus 14. Our derivative then is 6x squared minus 6x minus 36. Makes sense. That 14 should go away under the derivative. The 36 is all that should be left over. 2 times 3 is 6. 3 times 2 is 6. So this makes sense, right? Derivative checks out. We have factors of 6. So we can pull those out, and we can further factor out x squared minus x minus 6 as 6 times the quantity x minus 3 times the quantity x plus 2, and set this whole thing equal to 0. From this, we see that our critical numbers are negative 2 and 3. Now we're going to break up our number line from negative infinity to negative 2. That came from critical number up here. From negative 2 to 3 came from our other critical number. 3 to infinity, again, other critical number. And we're just going to take one x value in each of these intervals. So here we choose negative 3, just because first number that they chose. Here we choose 0, and here we choose 4. And you can pick whatever numbers you want. I would generally say pick something that works nicely with your math. If you have something that can make this, for example, 1, which is what they've done, great, right? Throw in negative 3 here, you're gonna get negative 1 out, right? Throw in 0 here, you're just going to get negative 3 times 2 times 6. Throw in 4, and this turns into 1. And that's how they're choosing these numbers. They're just choosing them because they make part of your polynomial 1, so the math is nicer to work with. Cool. So we're going to take each of these values now, and we're going to plug them into our derivative. Our derivative at negative 3 is equal to 36, which is positive. So our function must be increasing inside of this interval. Our derivative at 0 is negative 36, so our function must be decreasing in this interval because it's negative. And in this interval, at 4, our derivative is 36, which is positive, so it must be increasing. So now we know the general behavior of our graph. Let's check everything out. What our actual graph looks like is this. At our critical number, negative 2, we can see graphically that this is a max. And at 3, we can see graphically that this is a min. Now, using that test, we're going from increasing to decreasing. The test said that, in that case, negative 2 should be a max, right? And at 3, we're going from decreasing to increasing. So 3 should correspond with a min. And that is exactly what we see here. Everybody cool with that? So the test does in fact yield the right idea. And again, this intuitively makes sense if we think about just what it means to go from increasing, decreasing, to increasing. We have to change directions. So that must necessarily mean that that point where the direction changed was either a min or a max. So jumping to the next slide, if it'll let me. Oh, there it goes. We've got the function x to the 4th minus x to the 3rd. First thing we're going to do is take the derivative. So your function f of x is equal to x to the 4th minus x to the 3rd. Then the derivative of this thing, d dx, of x to the 4th minus x to the 3rd. This is going to come out to be 4x to the 3rd minus 3x squared, right? This is your derivative, f prime of x. Okay. Well, this thing factors. We can pull out an x squared. That's going to be convenient. So let's go ahead and pull out that x squared. Well, looking at this, we might be able to figure out where a 0 is in this inner term. But if we factor out a 4, it's going to make it a lot easier on us, right? So when we pull out that 4, this is going to be 4x squared times the quantity x minus 3 over 4. Now we're going to set this equal to 0. F prime of x is equal to 0 means 4x squared times the quantity x minus 3 over 4 is equal to 0. This tells us that x is either equal to 0 or x is equal to 3 over 4. Everybody agree? All right, so we know our critical numbers. Numbers, plural. Now, we're going to break up our number line according to that. This is x equal to 0. This is x equal to 3/4. So this interval should be from -infinity up to 0, but not including 0. This interval should be from 0 to 3/4. And this interval should be 3/4 up to infinity, right? Okay, now I'm going to pick an x value inside of here. Let's pick x equal to 1 or -1 inside of here. Inside of here, let's pick x equal to 1/4. And inside of here, let's pick x equal to 1. Seems like some reasonable numbers, right? All right, now we have to plug those numbers back into our derivative. Four times -1 to the second times -1 minus 3/4. This is equal to 4 times -7/4, right? We don't need to go any further because a positive multiplied by negative is negative. So this is less than 0. So automatically, we know now that we're decreasing on this interval. Plugging in 1/4, we're going to have 4 times 1/4, that quantity squared, times 1/4 minus 3/4. Well, this is going to be equal to 4/16 times, this is going to come out to be -2/4. Again, positive times negative, we're decreasing. Now we plug in 1. So plugging in 1 into our derivative, we're going to have 4 times 1 squared times the quantity 1 minus 3/4. This is equal to 4 times 1/4, which is equal to 1, and is greater than 0. So we must be increasing on this interval. Yep. Everybody cool with this? So I'm going to erase this here for a minute, just so we can kind of get an idea of what this graph is going to look like. So we have a critical number at 0, and we have a critical number at 3/4. On this interval, negative infinity to 0, we're decreasing. On this interval, 0 to 3/4, our derivative was negative again, so we're still decreasing. And on this last interval, our derivative was positive, so we're increasing. So our function appears to be decreasing, decreasing, increasing. Must mean that this is going to be a trough, right? In general, our function is going to look something like this. Something. Not exactly, no, almost exactly, yeah. Like that. So let's check all of this. Lo and behold, our function does in fact look exactly like that, right? But looking at our work compared to theirs, very first thing they did, took the derivative and factored out that x squared. They didn't factor out the 4 because they were lazy, I guess. I don't know. They didn't feel the need to factor out the 4. So from this, they set the derivative equal to 0 to identify our two critical numbers at 0 and at 3/4. They said, cool, we've got our intervals. Now we're going to check our x values. Question, why did they use 1/2 here? Anybody know?
Instead of 1/4.
Yeah. 1/2 squared is 1/4. It would cancel with that 4. So they did it just for convenience sake. But having said that, looking at, like I said, what they have, they found that we were in fact negative, our derivative was negative in this first interval, negative in this second interval, and positive on this third interval. So we must be decreasing, decreasing, increasing. Since the only time we actually change directions is between those last two intervals, we know that they must correspond to a max or a min, some relative extreme. And since we're going from decreasing to increasing, it must be that it's a min. And voila. So these derivative tests, they're helping us grasp some of this right away, right? Like I had no clue going into this what this graph looked like. But knowing we were going from decreasing, decreasing to increasing, and looking at this when x is equal to 0, our function had to be 0, and then we had to go through the origin, and then it had to be generally decreasing. Knowing just that little bit of information was enough to get the general form of our graph based off of our derivatives. So no longer do you have to go through and be like, all right, what is our graph at 1? What is our graph at 2? What is our graph at negative 3/4? What is our graph at pi? What is our graph? Like you don't have to go through and actually calculate out each one of these points. Now it's enough to know a handful of points and what your derivatives are doing. This was actually how a lot of old graphs were made. Now, as an example of where you're going to have one of those discontinuous derivatives, Let's imagine we have this function f of x is equal to 2x minus 3x to the 2/3 power. I'm going to have a discontinuous derivative here. So because your derivative is not going to be a polynomial, excuse me, it's going to be whatever this mess is. When x is equal to 0, this thing is discontinuous, it's undefined, right? This derivative is. So that's got to be a critical number. And whenever x is equal to 1, your numerator is 0. So 1's going to be a critical number. Those are going to be your only critical numbers. Lo and behold, those critical numbers happen to correspond with a relative max and a relative min. Now, again, just to make this point, not all critical numbers correspond to a max or a min. Here, this wasn't, right? But it was a critical number. Here, what we have on the board, on the slide, all of your critical numbers happen to be a relative extremum of some sort. So just keep that delineation, that distinction in your mind. Now, an absolute extremum, this is what an absolute extremum basically says, all right, you got an interval. What's the largest or smallest value in that interval? That's your absolute extremum. So here, we could chop our function up like this, right? And in this window, you have an absolute max and an absolute min. Your absolute max would be here, your absolute min would be here. But if we change this window just a little bit, like this, now your absolute min is here. Your absolute max stays the same, but your absolute min changed. So an absolute extremum depends only on the interval that you're looking at. Cool? So as a comparison, you have an absolute max. Your relative min happens to be an absolute min on this particular graph in this particular interval. And then you have a relative max as well. Notice your relative max and your absolute max don't have to be the same. The same is also true with your mins, but they could be the same, just like we had on the board. So as long as you have a continuous function, you're going to have on any given interval both an absolute max and an absolute min. And that makes sense, right? If your function is continuous, then your graph is a nice smooth line, right? And if your graph is a nice smooth line, then yeah, of course, somewhere along your graph, there's going to be a peak and a min. I mean, not a peak, but a max and a min. Cool? Dope. I knew that was there. For those of y'all who did not just see that, I did not almost just fall over a chair. Did not happen. So as another example, let's say we have the function 9 minus x squared. And we restrict it, we look just on the interval from -3 to 3. Well, we're going to have two mins. They both correspond with our endpoints. and we're gonna have one max. That corresponds with our absolute max, right? But notice, we know intuitively that this is not actually the minimum of your function, it's just the minimum on your function in that interval. Is everybody cool with that? Like if we had expanded this window to be from -4 to 3, then we'd have another min, right? Different set of minimums. And if we expanded it from -4 to 4, then we would have a different set of minimums, so forth, so on. So how do we find these? Well, the first thing you're gonna do is you're gonna go ahead and say, hey, what's my function at the endpoints, A and B? That's where I like to start. They have things a little bit different, but I like to start at my endpoints. Then you're going to say, all right, what are my critical numbers? What's my function doing at those critical numbers? What's the function value at the critical numbers? In this case, we're not looking at the derivative. We're just saying, all right, get those critical numbers. Now check your function at each of those critical numbers. Then compare that to your function at the endpoints. Then keep the largest and smallest y values, and you've got your max and min. Your absolute max and your absolute min, I should say. All right. This thing is a parabola. It's going to look something like this. So depending on where our window is, we might have two maximums, or we might have one maximum, right? We could have a window that cuts it off symmetrically. So, okay, yeah, then we have two max. Or we could have one that cuts it off asymmetrically. So, okay, we don't. Get what I mean? So taking the derivative of this to get our critical numbers, f of x is equal to x squared minus 6x plus 2. The derivative of this thing, f prime of x, that's equal to 2x minus 6. We can factor out a 2 to get x minus 3. All right, so our critical numbers then is going to be 3. So now, say, all right, what's our function at 3? F of 3 is equal to 3 squared minus 6 times 3 plus 2. This is equal to 9 minus 18 plus 2. So this is going to come out to be negative 11. Nope, my mistake, negative 7. Right? Now, we're going to check out our endpoints. F at 0 is equal to 0 squared minus 6 times 0 plus 2. That thing's equal to 2. Go. Now we're going to check at 5. F at 5 is equal to 25. My mistake, 5 squared minus 6 times 5 plus 2. This is going to come out to be 25 minus 30 plus 2. So this is going to come out to be -5 plus 2, or just -3. So, what's our relative max, our absolute max, absolute min?
Absolute max would be the 0, like F0.
Yep.
And then absolute min would be the 3. Did I say that right?
Not
0 and 3.
x equal to 3? Yes.
Yeah.
So, absolute max. That's the point 0, 2. Because there's no y value larger than 2, right? Absolute min. Well, that thing's going to come out to be 3, -7, right? Because there's no y value lower than -7. Not in that window anyhow. Relative max. Do we have one?
Would be good.
We would say we don't have one in this case. So relative max is only a peak or peak or a cusp. And relative min, what would that be? Well, since our absolute min occurred at a critical number, we know that that has to be a relative min. That would be 3, -7. So just to check everything, we've got the derivative of our function and finding our critical number. That was x equal to 3. Then we've got our endpoints, and we're checking everything. Well, 2 is larger than -7, -3, so it must be the max. So we know 0, 2 is the max. -7 is smaller than 2 or -3, so it must be the relative, the min, but also because it corresponds to a critical number, we can also say it's the relative min. It's a relative min, I should say. Is everybody cool with this? Folks at home, cool?
Yes.
Cool, awesome. All right. So for the sake of time, I'm going to jump through that and let y'all go ahead and take a 10-minute break. When y'all come back from your break, we're going to pick up with section 3.3.